So it makes use of commercially available polystyrene spheres of different sizes. You can name the size that you want. Okay? And there are self-assembly techniques that will allow you to stack this polystyrene spheres onto a substrate. Okay? And that's the OPTICAL structure. So once you have that self-assembled, you expose that to an ALD machine. In this case, you coat it with titanium dioxide. Okay? So now ALD coats whatever, as I said, is exposed. Right? So now you have these spheres all coated with titanium dioxide. Once you've done that, you calcinate. Basically, you try to melt the polystyrene spheres to get rid of them. Okay? So once you calcinate them, you get rid of the polystyrene spheres inside, and what you're left with is a structure consisting of this TiO2 that's in this particular pattern. Okay? And then you can do surface chemistry to coat this TiO2 structures with, say, quantum dots like cadmium sulfide quantum dots, and you can incorporate that electrode into whatever application you like. Like illustrated here is a dye-sensitized solar cell, but you can also use this for capacitors. Now, this is not just pictures. These are images of what these actual devices are. Okay? You can see that they look pretty much what's illustrated in the pictures in the series. Okay? All right. So storage. So there's a need for storage, right? Here is just a front cover of a magazine that illustrates, ALD that is used in the design of batteries for electric or hybrid cars. So storage comes in a variety of forms. You can either use capacitors, or electrical capacitors, batteries, or fuel cells. Okay? But what is common in all of this is three things actually. The electrode materials, you have an anode and a cathode, and then a solid state electrolyte, or a liquid electrolyte. But the trend now is for solid state electrolyte because there's always problems with liquid electrolytes. Okay. So ALD has there's a whole field of research associated with this. Again, I cannot go much into detail, but essentially this is how how these devices look like. You have an anode, a cathode, and an electrolyte in between, right? And so you want to develop materials for this. And the anodes and the cathodes, you want them to have three-dimensionality. In other words, you want to have cathodes with very high surface area because those are the ones that will store the charge, and that will determine the energy that will be stored in your capacitors. And we've done some of that electrode research, and this is using ruthenium and ruthenium oxide as possible anode for electrochemical supercapacitors. So the first thing that we did, of course, was we don't know, there's not a very well-known recipe for depositing ruthenium and ruthenium oxide. So this is a commercially available precursor. So you use this precursor plus oxygen to make these materials. And what we found is the following. Depending on the temperature that you're growing this, you can either get ruthenium oxide or ruthenium. So particular, if you are at, say, below 260 C, you get ruthenium oxide. When you're above 260 C, you get ruthenium. At around 260 C, you get a mixed phase of ruthenium and ruthenium oxide. And again, we identify that using X-rays, to be able to tell what we have in the films. Not only that, also depends on the substrate. Okay? Because in this case, for example, if you use silicon as the substrate, so we're doing this at 250 C, right? And supposedly, we should get just ruthenium oxide. It's not the case, because if you use silicon, bare silicon as the surface, you get ruthenium, not ruthenium oxide. Okay? Whereas if you have other surfaces like TiO2, titanium nitride, SiO2, aluminum oxide, you get ruthenium oxide. Okay? And this is going to be very useful. Again, you can now imagine utilizing this to make photonic structure, where you have alternating ruthenium and ruthenium oxides as the material. Okay? So now let me go back to characterizing this as electrodes for capacitors. So the way we measure capacitance is called, for the chemists, we just use cyclic voltammetry, right? So, and where the working electrode is our film, okay? And we do one complete cyclic voltammetric cycle, and the area here gives us a measure of the capacitance of the electrode, and that's given by this formula. So let's say, for example, in this case, when we deposited ruthenium oxide on a planar substrate, we get not so large capacitance, about 0.80 millifarad per square centimeters. Now, on the other hand, what about ruthenium? Well, if we start with ruthenium, what we discovered was if you do your standard cyclic voltammetry to measure the capacitance, that's this black curve here. But what we found is that if you go beyond 0.9 volts, in this case, you start oxidizing the ruthenium. Okay? And you do that, that allows you to get from ruthenium a ruthenium OX. We don't know what X is, but it's a ruthenium oxide complex with very good capacitance. So let's say, for example, if the standard ruthenium, we just get 0.16 millifarad, but if we oxidize this electrochemically, we get about 12.5 millifarad. Now, if you want to increase the capacitance, as I said, these electrodes, they require three-dimensional structure. We explored two types of structure. One is just, carbon nanotubes, and that you have capabilities here, right? So basically, this is just a spaghetti of carbon nanotube. So it's commercially bought, and that's dispersible in water. So you just spray it, and then to make a nice three-dimensional film that's illustrated here. The other electrode is polyimide, okay? And so what we were able to do is to develop a process to make three-dimensional thin pillars of polyimide. This is a cross-sectional SEM of those electrodes. So what we've done is to cover those electrodes with ruthenium and ruthenium oxide and measure whether there's any improvement in the capacitance once you go to these high surface area electrodes. And as you can see, indeed, if let's say, for example, you grow ruthenium oxide on carbon nanotube, you get capacitance as high as about 30. And for the one that was ruthenium oxide that was converted from ruthenium by electrochemistry, you get an even higher, about 40 in this case. Now, that's on carbon nanotube. Now, the one on polyimide, which is this structure here, you can see that the ruthenium oxide, you have just about 1. It's a factor of 10 improvement, but not very good. On the other hand, the one that was converted, the ruthenium oxide complex converted from ruthenium, that one gave us a very high capacitance, about 40 millifarad. So that's basically is what I would like to say. So basically, the bottom line is that ALD can be very useful for a lot of things, from very advanced semiconductor devices to energy storage and energy harvesting, things that are doable here. I think. So with that, I would entertain any questions.
Sir, siguro kung nahihiya pa yung mga bata. Oo na. So sinabi na sir kanina, you can apply this on type of substrate practically. So whether does it necessarily mean na it has, yung surface na yun should be atomically flat for the ALD to work? So it could be something like a porous material.
Yes.
Kasi nabagay yung expansion.
Right, just like this one.
That there are some cases that we're trying to
Oh,
explore
yeah.
right now, kasi sir, about porous ceramics
Sure,
being
sure.
coated with something inside the core.
Yes. Now that's been actually that's been done. There are hindi ko lang I did not show that. There are, for example, capacitors, right? So one of the things that you do is anodize aluminum, right? You have pores, okay? And then you want to make high surface area capacitors using that. So you can do ALD. You can use ALD to do that. In fact, both the metallization and the dielectric, and that's been done.
So if ever, sir, cost of this one as
The ALD.
kunyari sir, hindi tayo sa USD na lang.
Yeah. In fact, I told them how much it cost. Well, the system that I have is $150,000. Now, I know from experience that it's always, but when I mentioned this to Amy and Deb, they were not shocked. In fact, they told me to write a proposal. Maybe. So the idea is, if you want to set up something quick, you can just buy. But you can also build this. And I think if I'm going to pursue this in the Philippines, I would like to build it also because, as I said, there's an educational component to building stuff, right? But on the research component as well, you don't want to delay, potential groundbreaking research discovery because you're waiting. But to be very honest, also I think the procurement process takes such a long time anyway that probably doing it both ways they may end up, at your door at the same time.
So yung 150 US, that's just for the research. Ang lab na kumbaga.
Yes,
So
that's
the one you're saying
small.
on the
That's
camera.
small. That's small.
So
If you want the with plasma, because there are various techniques right now. I mean, there's really a lot of details that I skip. That one's called the thermal ALD. So essentially, your reactor mode is at some high temperature, but
So
nothing
it's
else.
some sort of vaporized siya and then it's a chamber.
Right. Now, but if you want to do some plasma chemistry also to enhance reactions, so there is plasma ALD. Okay? You can always buy that along as an additional capability. That one is more expensive. Probably a small system with a plasma capability would be maybe 200,000.
Those are for US prices.
Yeah, actually, you have to, from my experience, kamukha nila, when Arnel did the procurement for the solar lab facilities at NIP, and I was comparing the cost of the same equipment that I bought in my lab and that was purchasing here. It's a factor of 2.5 to 3 times more expensive here than in the US. I don't know why, but that's the reality. So that $150,000 multiply that by 3, so it's $500,000 almost. I don't know why it's so expensive.
So if we build it naman sir, anong level naman ng machining yung kailangan?
Well, if you're really, well, it's. I mean, really, what it is you don't probably even need to you can buy the vacuum pumps. In other words, you don't need to build the entire thing from scratch, right? You can buy, let's say, a Kurt Lester, you can buy, just a vacuum chamber, and then there will be minimal machining of for feed-throughs and things.
Ano vacuum requirements?
Pump down to mga 10 to the minus 6 core, but when it's actually pulsing, it's 10 to the minus 2, right? And then you need to buy bulbs, but what you need are pneumatic bulbs, so that they are fast. Hindi pwedeng solenoid. So, but those are standard.
Do you need a clean room? Kasi it's amazingly
Yeah.
small.
You need the what?
Clean room. So device applications are for you.
You really don't need to. It really depends on what you want. The ALD per se doesn't have to be inside the clean room. But if you're going to use it in conjunction with something, where exposure of the devices to air is, you probably need. But it doesn't have to be class 10 clean. So,
Plus,
not even plus 100. That's,
Yung lab sir sa baba.
One
Pwede na
minute.
yung plus 1 million.
yeah. Yeah, but, and of course, that's the vacuum part. But you need also the electronics to control it, and then the software. And what I offered Arnel and those guys is I actually have a separate controller that I can give away with the software. So I can have the vacuum system and we can make something work.
Any more questions? Questions from our guests?
natakot na. Pamanya siguro.
Or maybe they're hungry. Okay.
Okay.
That's it. Thank you very much.
So at this point, we'd like to thank our speaker. And I'll turn over the program. We'll organize.
So before we go, join me in awarding the certificate of appreciation to Dr. Danilo Romero. May I call the Dean and Sir Ian to award this. So let me just read some portions of the certificate. So this is a certificate of appreciation presented by the Lecturer Series Committee of the College of Science, UP Baguio, to Dr. Danilo B. Romero for delivering a lecture entitled Designing Novel Materials One Layer at a Time, Prospects for Electronics and Optical Applications, given on this 23rd day of June 2014 at UP Baguio. This is signed by the Chair of the Lecture Series Committee, Dr. Jericho Bacani, and the Dean College of Science, Dr. Rosemary Gutierrez. Sir.
Thank you very much.
Okay, thank you very much. Medyo maaga pa po kasi, pero meron tayo naka-allot na lunch. This is for everyone who attended the conference. So if you can wait until 11:30 probably, just please proceed to the College of Science conference room. Even our guests, we would like to have you there. We have guests from SLU. So if you still want to talk to Dr. Danilo, so you could just
I'm not.
have it there. Thank you so much for attending.
But there's